properties. Arenes are characterized by electrophilic substitution reaction. The first reaction is nitration. A nitro group is introduced into benzene ring when benzene is heated with a mixture of concentrated nitric acid and concentrated sulfuric acid, that is, nitrating mixture. For example, the reaction C6H6 plus concentrated HNO3 plus concentrated H2SO4 gives nitrobenzene, that is C6H5N2O. The second reaction is halogenation. Arenes react with halogens in the presence of a Lewis acid like anhydrous FeCl3 or FeBr3 or AlCl3 to yield haloarenes. Consider the reaction C6H6 plus Cl2 in presence of anhydrous AlCl3 gives chlorobenzene, that is C6H5Cl plus HCl. Sulfonation. The replacement of a hydrogen atom by a sulfonic acid group, a ring, is called sulfonic. It is carried out by heating benzene with fuming sulfuric acid, that is oleum. Consider the reaction C6H6 plus H2SO4 or SO3 on heating gives C6H5SO3H, that is benzene sulfuric acid, plus H2O. Friedel-Crafts alkylation reaction. When benzene is treated with an alkyl halide in the presence of anhydrous aluminum chloride, alkyl benzene is formed. Consider the reaction C6H6 plus CS3 in presence of anhydrous AlCl3 gives C6H5CS3 plus HCl. This is because alkylation with rearrangement 1,2 hydride shift during a Friedel-Crafts reaction. The reaction of benzene with an acyl halide or acid anhydride in the presence of Lewis acid yields acylbenzene. Consider a reaction C6H6 plus CS3COCl in presence of anhydrous AlCl3 or on heating gives C6H5COCS3, that is acetophenone plus HCl. According to experimental evidences, SE reactions are supposed to proceed via the following three steps. The first step is generation of the electrophile. The second step is formation of carbocation intermediate. The third step is removal of proton from the carbocation intermediate. The first step is generation of electrophile, that is E+. During chlorination, alkylation and acylation of benzene, anhydrous AlCl3 being a Lewis acid helps in generation of the electrophile, that is Cl+, R+, Rc + O, that is acylium ion, respectively by combining with the attacking reagent. Consider the reaction Cl2 plus AlCl3 gives Cl+, that is chloronium ion, plus AlCl4-, and also the reaction CS3Cl plus AlCl3 gives CS3 plus AlCl4-, and also the reaction CS3 single bond C double bond O single bond Cl plus AlCl3 gives CS3 single bond C double bond O plus AlCl4-. CS3 single bond C plus double bond O is known as acylium ion. In the case of nitration, the electrophile nitronium ion, that is NO2 plus, is produced by transfer of a proton, that is from sulfuric acid to nitric acid in the following manner. Step 1 involves H2SO4 plus HNO3 reversible gives H2NO3 plus HS4 minus. Step 2 involves H2NO3 plus reversible H2O plus NO2 plus, where NO2 plus is nitronium ion and is electrophile. In this reaction, sulfuric acid serves as an acid and nitric acid as a base. Thus, it is a simple acid-base equilibrium. The second step is formation of carbocation, that is rhenium ion. Consider the reaction C6H6 plus E plus gives C6H6E plus. The rhenium ion gets stabilized by resonance. Sigma complex or rhenium ion loses its aromatic character because delocalization of electrons stops at sp3 hybridized carbon. The third step is removal of proton. To restore the aromatic character, sigma complex releases proton from sp3 hybridized carbon on attack by AlCl4-. In case of halogen, alkynation and acylation, and HSO4- in case of nitration. Let's study about addition reactions. Consider the reaction C6H6 plus 3H2 in presence of nickel as catalyst at high pressure conditions give cyclohexane. Under ultraviolet light, 3 chlorine molecules add to benzene to produce benzene hexachloride, that is C6H6Cl6, which is also called gammaxane. Consider the reaction C6H6 plus 3Cl2 under ultraviolet at 500 Kelvin condition gives C6H6Cl6, that is benzene hexachloride, or BHC. Directive influence of a functional group in monosubstituted benzene. When monosubstituted benzene is subjected to further substitution, two types of behavior are observed. Either ortho and para products or meta product are predominantly formed. It has also been observed that this behavior depends on the nature of the substituent already present in the benzene ring and not on the nature of the entering group. This is known as directive influence of substituent. You can see here the ortho, meta and para positions relative to the substituent X. Ortho and para directing groups. The groups which direct the incoming group to ortho and para positions are called ortho and para directing groups. As an example, let us discuss the directive influence of phenolic, that is OH group. Phenol is resonance hybrid of the following structures given here. It is clear from the above resonating structures that the electron density is more on ortho and para positions. Hence, the substitution takes place mainly at these positions. Therefore, OH group activates a benzene ring for the attack by an electrophile. Other examples of activating groups are NH2 group, NHR group, NHCOCH3 group, OCH3 group, CH3 group, and C2H5 group. Meta directing group. The groups which direct the incoming group to meta position are called meta directing groups. Some examples of meta directing group are NO2 group, CN group, CHO group, COR group, COOH group, COOR group, SO3H group. Let us take the example of nitro group. You can here see the resonating structures of C6H5NO2, that is nitrobenzene. In this case, the overall electron density on benzene ring decreases, making further substitution difficult. Therefore, these groups are called deactivating groups.